I'm Connor Denomy from the University of Saskatchewan, and I will be presenting my poster, Enhanced Quality Control for Kinome Microarrays. The kinome is the sum total of kinase activity within a cell or cell population. Kinases execute the most important process in cell interaction and signaling, phosphorylation. As such, the kinome can provide insight at a deep level into which specific pathways are being altered in response to a treatment or disease. Kinome analysis is paired with high-throughput microarray technology. Phosphorylation target peptides are placed on an array and exposed to cell lysate and a phosphorylation detection method. Early investigations used software for nucleotide microarrays for downstream analysis, but there were significant limitations due to the differences between the technologies. To this end, the platform for Intelligent Integrated Kinome Analysis, PIIKA, was developed. Even after significant upgrades, there remains to be challenges. These challenges are shared with many other microarray technologies, and many possible sources of bias can affect experimental reproducibility and give inaccurate results. We've identified 3 important sources of bias that can affect kinome analysis results. And the first source of bias comes from the array image alignment software. When the software scans the image of the array, it identifies the features and measures the intensity of the pixels within those features. The area inside the feature is labeled as foreground and the area outside is labeled as background. The scanner software was designed for nucleotide microarrays, and because of that, it overestimates the size of the features when it comes to kinome microarrays. This causes background pixels to be labeled as foreground instead. The consequence of this is that it can dramatically affect results downstream. The mean intensity of the spot is lowered significantly lower than the true intensity, and the median intensity is lowered effectively to the level of the background. This is because the mislabeled background pixels quickly begin to outnumber the properly labeled pixels, growing as the spot size increases. The end result is that the skewness of the spot will be very high, with a small number of very high intensity pixels and a much larger of very low intensity pixels. Using this information, we can identify arrays that are in need of alignment. The mislabeling can be observed through a linear regression of the background corrected mean and the background corrected median of each probe. In this regression plot, there are 2 key features. Firstly, there is a dense shark fin region that is observable in the lower left of the plot. The slope of the linear regression is also lowered. A slope of 1 would normally be expected, but often the slope is much lower than that. So we can use deviation from 1 as a reliable indicator of misalignment. The second issue we aim to alleviate is the issue of outlier arrays. Many experiments, due to possibly unknown and unpredictable reasons, there are certain arrays that are dramatically deviant from other arrays performed in the experiment. Outliers can be detected by using pairwise distance between corresponding points on arrays, and then summing the distance between all of the arrays. Arrays with a significantly high sum of differences between all arrays can be marked as outliers. The third issue is that of positional bias. In kinome microarrays, signal intensity increases towards the bottom of the array. This is visible in the array images on this slide, where it is much lighter colored towards the bottom. This can be mitigated somewhat using background subtraction, but it is still present afterwards. Using the median background of the entire array to scale the background and foreground, we can come up with a better estimate of location bias to subtract. In this equation, we are scaling the local foreground, FL, using the local background, BL, divided by the median background of the entire array, BM. The same calculations are then done to the local background, which is then subtracted from the scaled foreground. So once we've identified these issues, what are the next steps? In the case of the mislabeled pixels, the only correction is manually readjusting the spot size in the microarray imaging software. Realignment of arrays is very effective at removing the fin and skewness effects, bringing the slope of the linear regression closer to 1. Removing outliers can vastly improve the results of downstream analysis. In this principal component analysis, the two arrays identified as outliers are highlighted in Figure A and then removed in Figure B. In B, the grouping of points in the PCA plot much more closely resembles biological reality. In this case, we have three well-defined treatment groups that should separate well into different clusters. Using background scaling, the effects of positional bias can be nearly completely eliminated. These plots show the correlation between the Y position of the array and probe intensity. In this case, a higher p-value, closer to 1, indicates a more effective reduction of positional bias. While background subtraction appears to be very effective at removing biases in most cases, the correlation between intensity and position remains very significant. Background scaling prior to subtraction completely eliminates this correlation in this case and many other cases. In summary, detection of arrays with overestimated spot size can be used to alert researchers to perform manual realignment, which leads to more accurate results. Removal of outlier arrays, as determined by pairwise comparison, can improve the results of downstream analyses such as clustering. Using background scaling can sharply reduce positional bias compared to using background subtraction alone. Thank you for watching my virtual poster presentation. I hope you enjoy the rest.